Welcome to The Explainer. Today, we're embarking on a pretty fascinating journey to master the modern cloud-native ecosystem. If you've ever felt totally overwhelmed by the absolute alphabet soup of modern software deployment, well, you're in the exact right place. We're going to demystify what's often called the DevOps Trinity: Docker, Kubernetes, and Helm. Let's dive in and explore exactly how these three fit together to power the biggest applications on the internet today.
But hey, before we get to the solutions, we got to start with a problem. It works on my machine. Man, if you're a developer, you've either said this yourself or you've had a colleague say it to you. It is without a doubt the most dreaded excuse in software development. You spend hours setting up Node.js, MongoDB, and Redis locally, and your app runs beautifully. But the second a new teammate tries to run that exact same code on their Mac or you push it to a cloud server, everything just completely crashes. Why? Well, because the underlying environments are just entirely different.
Okay, let's dive into this roadmap and climb this problem-solution ladder step by step. We'll start with the deployment problem, then look at Docker and containerization, scale up with Kubernetes orchestration, peek inside Kubernetes architecture, and finally, wrap things up with Helm, the Kubernetes package manager.
All right, Section 1, the deployment problem.
Getting code from your laptop onto a public server has historically been just a massive headache. Think back to the early Gen 1 days. You literally had to buy a physical bare metal server, plug it into a wall, and manually install every single thing. Then Gen 2 rolled around with the cloud, right? Places like AWS offering virtual machines. Definitely better, but you were still out there manually configuring dependencies. Every step solved the problem, but created a new one, which means we really needed a Gen 3 solution to get us true consistency and speed.
Which brings us to Section 2, Docker and containerization. And this brilliantly illustrates why Docker is the ultimate fix to that dreaded "it works on my machine" problem. See, with traditional virtual machines, you're packing this incredibly bulky, heavy operating system layer just to run one single application. It's huge and it's slow. Containers, though, they completely drop that heavy OS layer. They just share the host machine's kernel, making them super lightweight, lightning fast, and, best of all, perfectly isolated.
So when we're digging into Docker, there are two key concepts you really need to grasp, starting with an image. Think of an image like the ultimate blueprint. It's this packaged, shareable template that's got your application code plus every single library, tool, and dependency it actually needs to run. Whether you're running it on a Mac, Windows, or Linux server, the image remains exactly the same. You just pull these images down from public repositories like Docker Hub, and you're good to go.
Now, if the image is the blueprint, the container is the actual house built from it. It's the live, completely isolated running instance of your image. And get this, you can spin one up in milliseconds. Plus, because it's totally isolated, you can do whatever you want inside it, and there's absolutely no way it's going to mess with your host computer setup. But behind the curtain, the real wizard making all this happen is the Docker daemon. Basically, it's just a background service running quietly on the host machine. You send it a command, and the daemon is the actual engine doing all the heavy lifting, building, running, and managing those containers behind the scenes. So Docker is fantastic, right? You could run an app in a container on your laptop super easily. But imagine you're a massive enterprise like Amazon or Google. You aren't just running one container, you're running hundreds, maybe thousands of them. So how do we manage and scale hundreds of containers at once? What happens when web traffic randomly spikes? Or if a container just crashes in the middle of the night? You definitely can't have a human manually typing commands to restart them.
Enter Section 3, Kubernetes and Container Orchestration.
To handle that kind of massive scale, we absolutely need automation. And that is exactly where Kubernetes comes in, a solution originally inspired by Google's internal Borg project, by the way. The fancy technical term for this is container orchestration, because manually scaling servers during a traffic spike or healing crashed containers by hand is just literally impossible at scale. Orchestration completely automates the lifecycle of your containers, deploying them, scaling them up and down, and making sure they can actually communicate over a network.
Now, what's really interesting about this is the name itself. Kubernetes is actually a Greek word that translates to helmsman. You know, the person who steers a ship. It's honestly the perfect analogy. Picture a massive cargo ship completely loaded with shipping containers. Kubernetes is that expert pilot steering the ship, making sure every single container gets exactly where it needs to go smoothly.
But you might be wondering, why go through the effort of learning Kubernetes when cloud providers like AWS have their own built-in container services? Well, the biggest reason, by far, is preventing vendor lock-in. Kubernetes is completely cloud agnostic. You write your configuration for Kubernetes once, and you can seamlessly pick up your entire infrastructure and move it from AWS to Google Cloud or even to a physical server right in your office without rewriting your code. Throw in its incredible auto-scaling and self-healing stuff, and yeah, it's pretty obvious why it's the industry favorite.
All right, moving on to Section 4, Inside Kubernetes Architecture. Let's break down the nuts and bolts.
How does this orchestrator actually work under the hood? Well, before we look at the servers, we got to clarify one weird little detail. Kubernetes doesn't actually run containers directly. Nope. Instead, it wraps your containers up in a logical unit called a pod. A pod is the absolute smallest deployable unit in Kubernetes. Usually, it's just a one-to-one thing, one container inside one pod, but occasionally a few tightly coupled containers will share a single pod.
Okay, so a Kubernetes cluster is divided into two main parts. First up is the control plane. Think of this as the brains of the entire operation. So the crucial point here is the API server. That's your front door. When you want to deploy an app, you talk directly to the API server. It takes your request, stores it in a key value database called etcd, and then the controller steps in. The controller is constantly watching, making sure the state you want matches reality. And finally, the scheduler comes along and actually assigns your new pods to an available server to run.
And where do those pods actually run? They go to the worker nodes. If the control plane is the brains, these worker nodes are the muscle where the application actually lives. Every single worker node has a kubelet, which is basically an agent that constantly reports back to the control plane. It's also got kubeproxy to handle the network traffic, and a container runtime like Docker, for instance, which is the thing that actually executes your application.
Okay, so now you've got this incredibly powerful Kubernetes cluster up and running. But here's the final problem. Deploying even just one application like Prometheus or an Nginx server means creating dozens of super complex YAML configuration files. We're talking deployments, services, config maps, role bindings. It's a lot. Writing and maintaining endless YAML files for every single app is honestly an absolute nightmare.
Which leads us to our final stop, Section 5, Helm, the Kubernetes Package Manager.
Helm is quite literally the package manager for Kubernetes. Think of it kind of like apt for Ubuntu or NPM if you're a node dev. The real magic here revolves around something called a Helm chart. Maintainers will take all those dozens of complicated YAML configuration files required to run their app, bundle them nicely together, and publish them as a chart. And there are public repos out there hosting thousands of these ready-to-use bundles.
What that means for you is that installing a massively complex application takes literally 3 simple commands. First, you run helm repo add to connect to a centralized repository of charts. Next, you use helm search repo to find whatever app you're looking for. And finally, the magic words, helm install. Seriously, with just that one line, Helm automatically deploys all the necessary pods, services, and configs straight into your cluster in a matter of seconds.
Let's see how this builds out when you want to package your own company's applications. Helm separates your files so beautifully. You've got your templates, which hold those standard Kubernetes YAML files but with placeholders in them. Then you have your values.yaml file. That is where you inject your custom variables, like say defining 2 replicas for your staging environment or maybe 10 for production. It just makes reusing these configurations across your entire company incredibly efficient.
We've traveled a long way today, from the absolute dark ages of manually plugging in bare metal servers to isolating code with Docker, orchestrating massive scale with Kubernetes, and wrapping the whole thing up neatly with Helm. So I'm going to leave you with this final thought. Take a hard look at your own deployment pipelines. Are you guys still battling that "it works on my machine" curse, or are you ready to orchestrate the future? Thanks for exploring this with me today.